So there are two schools of thought here. When right, the question is when to introduce this topic, right? Should we do it alongside the PDF and the PMF and the PDF, or should we wait? Right. In my version of this course, I prefer to wait until we finish at least some modicum of description of the PDFs, then only bring in this, because I think it's more economical to do it this way. But in many cases, people might expect you to know this even earlier, but since anyway you're not, as long as you get it at some point in the course, I guess it's fine, right? So this is a very important idea which starts off looking very simple, but then quickly becomes more involved, right? So what we are trying to do is try to get a theoretical model for a long term average, right? A long term arithmetic mean maybe. For a time average. What do I mean by time average? So I'm just going to say consider a discrete random variable, some, let's say x with some with PMF Px, and let's say you take you do the underlying experiment some small n times. You say I equal to 1 to n, small n, b n independent realizations. This is the standard setup in probability theory, right? That is n realizations or observations, whichever way you want to call it, right? Its value that it takes in any trial is either a realization or an observation. Both terms are used, right? Especially the word realization, you should, right, be comfortable with that. Okay, so of course, I mean in probability repeated trials are always considered to be independent, never, right, dependent. So if these are n observations, so this is basically now a time series, if you think of it that way, right? You assume that at one instant of time you can only take one observation, so therefore you take n of them, you can string all of these samples along the time axis, right, and you get a wonderful discrete time sequence, the xi essentially. So now if I want to calculate this average, let's call it what should we call it? So let's not call it anything except average. So let's say then define the average as the sum of xi, simple average, right? If you do this, average equal to right, xi by n. Is there a theoretical model for this? So this can be calculated only if you know these observations, but a priori, without doing any calculations, without doing any experimentation, right? Can you model this long term, this kind of an average especially for large n? So is there a model for this? And the answer is yes. It is a so called expected value, which you can write down in terms of the probabilistic description Px. To understand that, let's say you divide this sum. I'm specifically saying it's discrete to make things simpler. So each of these x sub i's has to be one of the values of x, right? And of course we have used this xi in a different way earlier. We have used it to describe, right, x1 to whatever xn to be the n possible values. Now n is a totally different number here, it's a time series, right? But supposing, instead of writing it, let me just sort of try to verbally explain it. Can you not group this into the first value plus the second value plus the third value and so on? Let's say your x is the outcome of a single die, so you have only 6 possible values. So let's not confuse the 6 and the n. So this is x, each of the xi is only going to be a number, let's say from 1 to 6. So I split this, right? Instead of just doing it as 6 plus 1 plus 3 plus 4, and let's say I pull all the 1s to one side, I pull all the 2s in the middle, and then like that. So I can always write this by splitting the numerator, isn't it? And then for each of them, which is one value of x, if I, what will that be? That will be some n1 times that value x, and then you have an n, capital small n in the denominator. So if you look at that portion of this fraction, it will tend to px of that value as n becomes large, multiplied by the value that you multiply, the random variable is taking. So I am just saying, I am going to say that the model is basically this. For a discrete random variable, I want you to look at this theoretical sum over all possible values that x can, capital X can take, x element of omega x, right, PMF Px, and then of course you have omega x also, right, which are the set of values that x, capital X takes, right. So the model for this average is basically, I am claiming, is exactly this. Of course these two are not going to be equal, right, this is some random quantity which can keep fluctuating, but the claim is that if you make this n large enough, and if this, right, if x actually has this probabilistic description, right, if this is, then these two should get closer and closer as n, or this should, right, the fluctuation of this should decrease as capital N increases, and ultimately this should become very close to this, as if you make this n go to infinity. For example, if you do this with the die experiment, you what answer will you get? You get 3, is it 3.5 or what is it, if you say each phase is equally likely, 3.5, right. So this number, this long term average of sum of average of all the die rows should approach 3.5, which is this 1 by 6 plus 1 into 1 by 6 plus 2 into 1 by 6 plus 3 into 1 by 6 plus 4 into 1 by 6 plus 5, right. So what is the, so if you pull all the 1 plus 2 plus 3 plus 4 plus 5 plus 6 is 6 into 7 by 2, which is 21 by 2, that divided by 6 is 21 by 12, which is 3.5, sorry, 21 by 6 only, not 21 by 2, 21 by 6, 3.5, right. So that is why we are motivated. I don't want to, the thing is this time series is only a step, so don't get confused. Maybe this notation is not the best. I should have put, like the DSP textbooks do, I should have put what? This I in bracket as a parenthetical thing rather than as a subscript. That would have actually cleaned up this, but I didn't do that, so I don't want to go hack the blackboard at this point. Anyway, we're not ever going to, in this course, consider this thing any further. The time series argument we don't consider in this generally. I brought it in only to motivate this for a discrete random variable. This is clear. So the sum and substance of what I am saying is basically this, right. The so called mean or mean value, we write as E is now going to represent an operation, the operation of taking a statistical average. I am rewriting that thing exactly so that it's very clear without any, right, any of the, this is not clear what I have written here, I have copied it back here again. So I want to and we also call this as equal to mx. There are two right, this E is a multi-purpose, as we will see, it's a multi-purpose operation symbol, but this m is very specific to mean, this right. We do not, we just take exactly x here, multiply by, weight the value that x, the value by the probability of x and add. That if we just do this, we call, it's mx, we also write it as E of x. Now you might wonder why you want to write in such a complicated fashion, but there is will become very clear before the end of today's lecture, right. So this E is, right, is like probability, right, in that sense, it's an operation, probability is defined as a function, but this is and you use the random variable name, that capital X, you put that within the parentheses, right. So this is the basic fundamental definition of the mean value, and it turns out this is one of the, right, it's one of the most useful extensions of the theory. Just for doing probability calculations, we just added only probabilities, right, and of course if you leave this X out, you obviously will get 1. But by putting this X here, it turns out you can get a much richer theory, and that is what we are going to be studying almost virtually the entire rest of the course. Okay, fine. Is this okay for everybody? So this is for a discrete random variable. Let me also write out what do we do when it's continuous. Unfortunately, in the continuous case, right, you can't so easily talk of the probability of x taking the value small x, because that is going to be 0, but instead you look at some small interval around that number small x. So I am talking of purely continuous x. I am going to say, for lack of time, I cannot look at the most general definitions possible here, right. That is the case of that waiting at a traffic light where you have finite probability at x equal to 0 and all that. I leave you to figure out how to calculate the means and other things for that particular type of distribution. I am going to say up front, right, we are only going to consider 2 classes of random variables in this class. Either they are purely discrete or they are purely continuous, right, but we just do not have the time to take off on other excursions on other type, the so called mixed type. Okay. So for purely continuous x with PDF fx, here also nobody is going to prevent you from doing this kind of a calculation, right. You can if you spin a pointer, each time you get some small xi, nobody is preventing you from running that experiment n times and taking the average. So what is a mathematical calculation you can do with this PDF fx, which will be a good model for this average, and it turns out that that average is basically defined as an integral of this. You integrate over the set omega x. Now why does this integral make sense? Because what is this fx x dx? It is a probability of getting that small value, getting a value of small x, I mean an interval around that small x, either x to x plus dx or whatever. So what you are doing is you are adding all those, you are taking this probability, multiplying by this x, and then adding. This integral is nothing but addition. So you can think of the Riemann sum version of this, which is a sigma over small intervals, and then as you make the interval width go to 0, the sum becomes an integral. So it turns out this is exactly what we want, right, in the case of a continuous random variable, right. So the calculus is our wonderful savior in all of these things. So you can think of averaging even when you have a continuous function of x, it does not have to be just a discrete function. And I think this kind of integrals you may have seen in earlier, like when you do moment of moment of inertia, or find a center of mass or something. Did you ever calculate center of mass for a distributed mass? Did you not do integrations of this kind? So it's an analogous to that. So are these definitions very clear? Please take the time out to understand them, because they will be crucial to our future, all future work in this. This is okay. I don't want to just look at this section of the, I want to exclude them and look at you people also. Is this all right? Okay. Okay, now before we proceed again, that as long as this omega x is finite in some sense, there is only a finite number of points in omega x in the discrete case, and this omega x is a finite length interval here, there is no problem about the existence of Ex. But if you make this omega x go to infinity, either countably infinite or infinitely long, it turns out that there is no guarantee that Ex will always exist. So you can easily come up with examples of fx which are valid PDFs which do not have expected values, because the sum does not converge. So, Ex need not always converge, right. One of the simplest examples is to take the 1 by x squared PDF. One by x squared for x greater than 1. This is a valid PDF. How did we get this? We got this by taking a uniform random variable from 0 to 1, u0 1 and taking 1 by x, right. That had this PDF 1 by x squared. You try sticking this definition into that, omega x is now the entire interval from 1 to infinity. Will that integral converge? No, it will not, right. It does not converge because you get an integral of ln x, you get ln x evaluated from the limits 1 to infinity, and clearly that that does not have any, it is not finite. So, so clearly this, right, we have to therefore be careful, right, this is one thing. There is also another problem that we have to address, and that is two infinities cancelling each other, that is 1 plus infinity cancelling a minus infinity. That is also something we have to avoid, because that also makes, right, makes this a very poor mathematical model in case, right, you get some situation of that kind, right. For example, if I take the Cauchy, this is a classic example. 1 by pi into 1 plus x squared, I think is the easiest Cauchy I can think of. No alpha parameter or whatever, right, it is just simple Cauchy. This here of course you have minus infinity to infinity. Now you, right, stick this inside this. Now omega x will go all the way from minus infinity to infinity. Now you tell me if that integral should exist or not. How will you decide if it exists or does not exist? X divided by 1 plus x squared dx, right. Does that integral exist from, if you integrate from minus infinity to infinity? The answer is no, it does not exist, simply because you have, if you say that the value is 0, you are actually implying infinity minus infinity is 0, which is not correct. And in fact you can test it out with an experiment. You know, the problem set 6 talks about how to generate Cauchy random variable from uniform. You write a program to do that, take some long term samples, long term average with that Cauchy sequence, right, and then see if this guy converges to some value, converges to 0. It will not. This experiment has been done and it has been reported, so let me save you the time and effort, but of course you are free to simulate if you want to simulate. But if you do this when xi is a samples of Cauchy, you do not get 0. It will just go, the average will just jump all over the place, it will not converge, no matter how large you make n. So you shall not do, so what I want to say is you shall not take infinity minus infinity and set it equal to 0. Why do I get infinity minus infinity, right? I get infinity minus infinity, so let me write it here. If I do, if I consider Ex as, let us say, a limit as some, what should I say, some x, what is our standard notation for some large real number? Call it, okay, call it x naught going to infinity, something. I need some number, right? What do? If I do this, put a question mark here, big question mark. If you do this, yes, it will always be 0. If you integrate from minus, forget about this limit, right? This integral will go to 0 if you do from fixed minus x naught to plus x naught. But if you make this minus x1 to plus x2 and allow infinity to be reached independently, separately here and here, then you see that the integral is undefined. So this is not equal to 0. when if you change this to minus x1 and this you change, let us say to x2. It's actually undefined. So how do we get a mathematical statement of existence of the a test, let us say, for the existence of E of x, right? So it turns out that for whether it's a discrete case or the continuous case, you can easily come up with a discrete counterpart of this, right? All you have to do is consider the PMF 1 by 2 k squared or something from 1 to infinity and minus 1 to minus infinity. It's extremely simple to do that, right? So, so basically whether it's discrete or continuous, right, we make this here. Ex exists if and only if, that is IFF is if and only if E of mod x exists. Now what is the meaning of this E of mod x? That is, maybe I should not have, i.e. this sum converges. So forget about mod x, this notation for a second, just think of this and this, right? Forget about this, just in this definition replace x by mod x, in this definition also replace x by mod x. So the condition for this Ex to exist is that the corresponding sum or integral be absolutely summable or absolutely integrable. This sum itself can be positive or negative depending, I mean the individual components here, the sign of this x tells is their problem here. This is always non-negative. So how do you ensure that this whole thing is going to be positive? You just change this x to, or you take the absolute value of the whole thing, which is simply mod x times this. So you want that sum to be finite. Why we call that E of mod x I will come to a bit later. So let us leave this aside just for a second, just think of this. So if this is fine, then you say that E of x exists. This is just a simple test, right, nothing more than that. And you can obviously see that if I put mod x here, no matter, even if I put minus x0 is still not going to converge. It's going to infinity, right? Isn't it? It's very clear that you no longer get positive infinity cancelling negative infinity, both are negative x and positive x, you get plus infinity and it will happily diverge, so no problem. So in that sense, so you don't get this ambiguity of whether it's going to if it's going to 0 or not. So this is just a warning, right? I mean this is an important enough it's a thing which I have to say. So basically, and the fact is that we do deal a lot with Cauchy PDFs, right? The Cauchy PDF has a very strong tail, right, which is falling off only as 1 by x squared, and no PDF which has a tail which falls off as 1 by x squared has a mean value, whether it's one sided like this or two sided like this. This is clear, that is all I want to say. So basically what is the take home message from all this? The PDF should die down somewhat, should die down faster than 1 by x squared, should go to 0 faster than 1 by x squared. 1 by x squared may be sufficient for the PDF itself to be integrable, but when you multiply by this x, the resulting function is no longer integrable. I mean the integral is not finite if you go all the way to infinity.